Well, first things first, we're going to go to our introduction. We need to talk about what is the Lorentz force. Whenever we have a charged particle submerged in an electromagnetic field, we know that the force which is subject to has expression given by equation number 1. This equation is known as the Lorentz force. However, if we focus on the case when there is only a magnetic field, equation number 1 turns into equation number 2. From equation number 2, we know that the force is proportional to the speed and the magnetic field which the particle is subject to. In order to obtain an ODE from which we can part, we need to use Newton's second law. By applying this law, we get the right-hand side of equation number 3. And from here on out, we need to decompose everything, since we are dealing with a 3D problem. So, if we part from the conditions given on equation number 4, where do note that the components of the magnetic field may vary in space, by decomposing everything, we get the so-called equations of motion for our particle. But here we have a little problem. We don't have any method to solve this system. So what can we do? It turns out that we may transform the system into 6 first-order linear equations, which we actually do know how to solve. And so, if we have the initial position and the initial velocity, we will be able to obtain the dynamics of our system for any magnetic field that may only vary in space. Now we go to the numerical background and methodology. Starting with our numerical background, we first need to recall what the Runge-Kutta method of order 4 is for a first-order equation. If we have an initial value problem that is well posed, then we may use the Runge-Kutta method in order to approximate the solution y at the given interval at n+1 equally spaced points. Then, if we set h, our step size, t0 and y0 as what we see on the slide, we are now able to compute what the essence of this method is. The k1. We are now able to compute the essence of this method. We are now able to compute what the essence of this method is. K1 to K4, which are defined as we see on the slide. By taking a closer look to the definitions of Ki's, we see that these are just the slopes of y at different parts of the interval between Tn and Tn+1. And then we get our approximation as the weighted average depicted on the last equation. Moving forward with our numerical background, we need now to consider how to solve a second-order ODE. If we consider a second-order initial value problem, we need to basically rename and transform the system into a 2 first-order differential equations. We have a clear example in the slide, and now we turn this into a solvable problem. Now, moving on to the methodology we'll use to solve this problem, we need to talk about the Runge-Kutta method for 6 first-order ordinary differential equations. It's important to say that we are going to display the algorithm, and this algorithm was taken from the Burden book.
We now enter the analysis and numerical results section, where we consider several scenarios of a charged particle in the presence of a magnetic field and find numerical solutions for its position and velocity in the time interval between A and B. Particularly, the first 2 scenarios focus on a constant magnetic field, while the final 2 focus on a magnetic field that is variable in space but constant in time. Note that all of these scenarios are conservative since there is no current or electric field, and therefore, from Ampere's law, the magnetic field is irrotational and so is the force field. These numerical solutions are found with our implementation of the Runge-Kutta method of order 4 for a system of 6 linear equations with n iterations in Python. With this method, we will also see how a large time step relative to the motion produces very inaccurate results due to an unexpected numerical dampening of the charged particle's motion. That is to say that our numerical solutions will not conserve the energy of the system in this case. So, we begin in the first case, where we consider an electron in the presence of a constant magnetic field of 1 times 10 to a negative 10 teslas in the k direction, with an initial position of 1 meter in the I direction, 2 meters in the j direction, and 5 meters in the k direction, and an initial velocity of 1 meter per second in the j direction and also in the k direction, between interval from 0 to 2 seconds. This means that the charge is negative 1.6 times 10 to the negative 19 coulombs, and the mass is 9.1 times 10 to a negative 31 kilograms. In this scenario, we expect the electron to engage in counterclockwise circular motion in the I and j directions while traveling at a constant velocity in the k direction. These are the position versus time and velocity versus time plots of our solutions in each direction. The k direction does in fact show a constant velocity. Also note that the plots of the I and j directions oscillate with the same frequency and are out of phase, relative to each other, by a quarter of a period. This is indicative of the circular motion that we expect. We also expect the velocity versus time plots to look like the derivative of the position versus time plots and feature the correct starting velocities. The trajectory plot confirms the circular motion and features the correct starting position. Here, we can see the phase space of each direction. For the system, it means that we're plotting the velocity versus position in each direction. This is a very useful space where we can fully analyze the dynamics and energy of the system in each direction without having to look at the individual position versus time, velocity versus time, or trajectory plots from before. Note that oscillatory motions in a particular direction correspond to a rotation in that direction's phase space, since a positive position with a zero speed evolving into a zero position and a negative speed traces an arc in quadrant 4. A zero position with a negative speed evolving into a negative position and a zero speed traces an arc in quadrant 3. A negative position with zero speed evolving into a zero position and a positive speed traces an arc in quadrant 2, and a zero position with a positive speed evolving into a positive position and a zero speed traces an arc in quadrant 1. In the second case, we consider a proton in the conditions as the electron from scenario 1. Now the charge is positive 1.6 times 10 to a negative 19 coulombs, and the mass is 1.67 times 10 to a negative 27 kilograms, much more massive than the electron. We expect the proton to engage in clockwise as opposed to counterclockwise circular motion in the I and j directions while traveling at a constant velocity in the k direction. For the plots, we will only note the differences between this scenario and scenario 1. These are the position versus time and velocity versus time plots of our solutions in each direction. We now have the expected circular motion, but in the opposite direction, with a much larger amplitude due to a mass of the proton. Nothing on this one. The trajectory plot again confirms the circular motion in the opposite direction, with a larger radius. The phase space of each direction comes out as expected, with rotation in the I and j directions indicative of oscillation in these directions, and a constant velocity in the k direction. We return to scenario 1. An interesting effect occurs when a relatively large time step compared to the motion is selected. If we run our code with 20 iterations instead of 200, we have a time step of 0.1 seconds instead of 0.01 seconds. In this case, the accuracy of the Runge-Kutta method of order 4 rapidly declines. Particularly, with the trajectory plot, we can appreciate how quickly the numerical solution veers from the expected result. The phase diagrams for the I and j directions show the presence of an attractor, which indicates that the numerical method is not conserving the energy of the system. Only the phase diagram for the k direction is accurately displayed, either because it undergoes no acceleration or because it does not feature oscillation.
Now consider the case in which our magnetic field is not constant in space. For this, we have to consider Gauss's law for magnetism. For both cases, we kept the initial conditions the same, and also we kept the electron as our test particle. Now, for our first example, we consider this vector space as our magnetic field, and the plot is given below. We can see at the beginning that the path is not really defined. However, as time goes on, it starts seeming like an helicoidal path. Now let's look at the graphs. The first row corresponds to the position versus time plots, while the others correspond to the velocity versus time. In the case of the position for the x and y axis, we can see that in fact the path is oscillatory. Now let's go to our second example. In this case, we chose this vector space as our magnetic field, and we can see in the plot that the trajectory is very interesting. Now let's look at the plots for this example. They are organized in the same way as the other. But if we consider the position versus time plots, we may think that the path becomes uniform as time goes on. However, this is not the case for this example. In fact, if we simulate the trajectory for 15 seconds, we can see that the path becomes more and more chaotic. And if we look at the plots, at least the position versus time plots, we can see that there isn't a single pattern in which we can rely on in order to predict the future movement of the particle. Now, we wanted to present this example because we wanted to show that not every single problem that we solve is as elegant as previous simulations. In fact, this is where numerical analysis plays a huge role in order to predict future behavior of a particle. Now let's dive into the conclusions. First of all, we want to say that theoretically the problem wasn't really complicated. However, choosing the correct system of equation was. In this case, we saw that using a system of six equations was better than using a system of 3 equations, with the little disadvantage that we had to use a very high number of mesh points. Lastly, we want to say that numerical methods can deal with relatively complex problems, such as real-life problems. And this is it for our presentation. I hope you enjoyed it and learned something from it. If you have any question or comment, please let us know. Thank you.